Okay, hello everybody, and welcome to today's class. In the last lecture, we started the discussion of curves and curves integrals. And of course, today we continue that discussion. Last time we finished with some physical example, or physics-inspired example of a curve integral. What is the meaning of a curve integral? What I would like to do today is continue the discussion with a few further examples that demonstrate a few properties, that illustrate a few properties of curve integrals, which are somewhat different from the usual integral over intervals. Then, after that, we take a look at some mathematical aspects of the entire theory, some deeper mathematics, and then we take a look at also a few other physics-inspired examples, a few applications, so to speak. And depending on the time that we have left, we will talk then about integrals of vector fields. So let's hope the audio works. And in fact, let me use the empty slides instead. So I would like to discuss two examples. So I would like to take a look at two examples. Let's say we have basically what we need to do is we need to distinguish between the curve, the geometric curve, and the parameterization of the curve. And that will be illustrated with the following example. So generally speaking, we need to distinguish between gamma, small gamma, the parameterization of the curve. Let's say we got gamma going from A to B into R to the n. And then the image of the curve, the geometric object itself, which is described by this parameterization. And remember, we called that image by capital gamma, which is some subset of R to the n, some one-dimensional curve that floats through R to the n. And generally speaking, there are always many different parameterizations for each curve. Many different parameterizations, we call them all gamma, describe the same geometric object. They describe the same geometric curve. Okay, let's have a look at, again, some very simple example, two different parameterization of a straight line. Let's put the first one in blue. In red, I mean. First, we take a look at a parameterization having the interval from 0 to 1, going into R to the 2, and it maps, well, it's very simple. T, the parameter T, is mapped to 1 plus T in the first coordinate and 2 plus T in the second coordinate. So that just describes a straight line starting at 1, 2 and going up to 2, 3. The second thing does another curve. All our curves are called little gamma here. This time are parameterized from 0 to 2 pi. Again, I go into R to the 2. But this time I map T to something slightly different. Namely, I map it to 1 plus sine of t plus 2 plus sine of t. So it's just two different parameterization of the straight line. The straight line from 1, 2, we start at 1, 2, and we go to 2, 3. Okay, and just to get a feeling for this, if I've got a straight line, I have this. The first one is a very uniform parameterization. Starting at 0, going up to 1. And the second one will be a parameterization going from 0 up to Oh, well, I need to fix one thing. excuse me, that should not be 2, it should be pi over 2. But on that, we start at 0. Then, okay, the sine goes from 0 up to pi over 2. But if we try to set marks along that line, it will first go up fairly quickly, and then if we set equal dots on this interval from 0 to pi over 2, and kind of plots them along the straight line, then we see that first we move fairly quickly, but then the speed gets slower and slower. Okay, we will try to compute a curve integral of a function along this interval, but we will see that, okay, we've got two different parameterizations, but we will obtain the same result. Okay, let's then start with the first one, the parameterization from 0, 1, and we consider the following function. F goes from x1, x1 and f2, f goes from x1 and x2, and just produces the product of the two coordinates. Very simple. And we use the curve integral using the first parameterization. So that's straight parameterization, t being mapped to 1 plus t and 2 plus t. Let's see what happens. So we got the integral along gamma of f, dl. That's how we write our curve integrals. And by definition, it's just the integral from 0 to 1. So we got the integral from 0 to 1. The path is, the function that we integrate is f of gamma t multiplied with the speed of gamma at parameter t. That's the definition of the integral. Okay, and we know that, well, f is just the product of the two coordinates. So what we do is we plug in the values of the two coordinates depending on the parameter t. This is our x1. This is our x2. So on the one hand that. On the other hand, we also need the speed of the curve. Fortunately, in this case, it's very simple. Gamma t, okay. If you take a look at the curve, you can immediately see what is the derivative of the curve. If you just take the partial derivative of the two coordinates, you just get the vector 1, 1. The speed is constant. We've got constant speed, and we can 1, 1, and we can easily see that the magnitude of the speed is always the same. It's always the square root of 2. 1 plus 1, and then takes the square root. Okay. With that, we have transformed this curve integral. We have written this curve integral now in terms of the standard integral that we already know from analysis 1 and 2. It's just an integral over the interval from 0 to 1. Okay, and multiplying everything out. Okay, we can pull out this factor of square root 2. And if you multiply out internally, what we get is just some polynomial, 2 plus 3t plus t squared. Then with this factor of square root 2 pulled out. And eventually, then we just use our standard calculus methods. We compute the antiderivative, and we evaluate that at the points 0 and 1, giving us the following final result. Square root 2 and 3, 5 over 6. Okay, so we just applied the standard method of calculus. We applied the definition of the curve integral and the standard methods of calculus to get there. That's all. We would like to compare this with a second parameterization of the same curve, where we did not have a straight line, but instead we had this parameterization using the sine function. So we have the second parameterization, the function that we want to integrate is still the same. Just f of x equal x1 times x2. Just the same. This time use a slightly different parameterization, going from 0 to pi over 2 to r to the 2. And t is mapped to 1 plus sine of t and 2 plus sine of t. What I do now is I use the same method as before. Okay, we have got our curve integral. We integrate the function f along the curve, giving us the integral from 0 to pi over 2 of f gamma t. And we multiply it with the speed. Now, a number of things need to be done here. First, okay, what is the speed of the curve? It's an important question. We need the speed of the curve. So we look for this vector, the derivative of the curve. And fortunately, it's very simple. What is that? Someone have a suggestion? Yeah, please. Yeah, just cosine of t in both cases. It's a very simple example. So the speed is a cosine of t in both cases. Corresponding to that, the magnitude. Okay. In both cases, we've just have the cosine. And, well, we get, technically, if we write this down, we get the cosine of t squared plus the cosine of t squared. Takes the square root, which evaluates to square root of 2, and again, then the cosine of t. Fine. So with that in place, we can now plug in the function values of f, the values of the curve and the speed, and we get the following integral from 0 to pi over 2. We get the integral of 1 plus sine of t, that's the first coordinate. We get the integral of 2 plus sine of t, that's the second coordinate. And then the speed parameter here, this vector corresponding to the speed, square root of 2 times the cosine of t. Now, this looks a bit complicated, but in fact, we can reduce it to some integral we've just seen before, namely just using the law of substitution, integration by substitution. Namely, okay, when we take a look here, you would like to replace the sine function by, you would like to put this into a variable. And let's say, okay, the variable u is the sine of t. Okay, if I take the differential of that, d of u must then be the cosine of t times dt, just applying the law of substitution. And then I see I can vastly simplify this integral because, okay, cosine of t dt, that's already here. So I can replace that one by du. Similarly, I can replace the sine of t by u. And then it's the very last line. Again, I get the integral from 0 to 1 of 1 plus u times 2 plus u times the square root of 2. So some integration techniques that you should be familiar with. And we just computed the value of that integral before. So that's very simple. We've just shown that the two integrals, the two parameterizations of the curve, give us the same result. Okay, and that is true for basically any parameterization of the curve. If you've got any differentiable curve, little gamma, these curves all describe the same geometric object. If the curves describe the same geometric object, then no matter what parameterization you pick, the curve integral of a function along that curve will be the same. So let's summarize these observations. So if gamma goes from the interval from a to b to r to the n, if you've got such a curve, if that curve is simple and regular, then the curve integral along the geometric object gamma only depends on the geometric object itself. It does not depend on the parameterization. And arguably, that's exactly what should be done. That's exactly what we want. Because the parameterization is in some sense arbitrary. Like the physical object, the physics, so to speak, is all incorporated, all included in big gamma, in the curve itself. Gamma is just a parameterization, and it's just a mathematical tool. Just a mathematical tool in order to formalize the integrals. There's typically no intrinsic physics in there. And, okay, in the last example that we've seen, we saw that changing the parameterization corresponds to a change of variables. That's an important observation because actually changing the parameterization is nothing but a change of variables in an integral. So changing parameterization corresponds to a change of variables in the integral. There will be a few exercises about this too. And I think after a few exercises you will be more comfortable with that. Take some practice, but after some time this will flow quite naturally for you. That was some discussion about changing the parameterization in the curve. Now let's take a look at some other mathematical aspects of this. So let's do some theory here. So we remember that integrals were defined in terms of Riemann sums. Just as a refresher, just in case, if I got an integral over some interval from a to b, so how again did we define the integral? We had a function f that is defined over this interval from a to b, and the integral was defined using a Riemann sum. You've seen this, I think, in analysis 1. You take these little columns here. You take a function value, and then you put together these columns, and so on. I think you remember at least this picture. And then, okay, you take finer and finer resolutions. As you pick this interval, these subinterval size, smaller and smaller, then eventually you get a limit value. That will be the area beneath the curve, the area under the curve. And that was, we remember, that was the definition of the integral. We try to do the same now with integrals along curves. That will be, in some sense, a mathematical justification why we take that definition of the curve integral. So whatever the value of the curve integral should be, it should be the limit of a Riemann sum. So if you have got this integral of gamma of f, the integral of f along the curve gamma, okay, it seems intuitive if we have got this definition here of the Riemann sum from analysis 1, then the natural correspondence in the case of curves would be, okay, I take some curve, and then I take parameter points. I take a subdivision of the parameter interval from a to b. So explicitly, I take this interval from A to B and I pick points there. In this case, for example, 6 points. Okay, then it seems intuitive that I can approximate the value of the integral of f along that curve by, in some sense, approximating the curve by succession of straight lines. So what I've done here, okay, I start at P1, I take a straight step to P2, I take a straight step to P3, I take a straight step to P4, P5, P6. If I increase the resolution and take more and more points on the interval, on the parameter interval, then I get a finer and finer approximation of this curve by little straight lines. Now, the idea of the Riemann sum here is I take the function at P1, and I say, okay, approximately along the first interval here, the function will be the same as fp1. Along this interval, the function will be the same as fp2. Along this interval, it will be the same as fp3, and so on. And then I do the same principle as I've done for the Riemann sum. Because what I did here with the Riemann sum, okay, if I've got P1 here, P2, P3, then in the definition of the Riemann sum, here I just said, okay, on this is roughly always the same as fp1. Here it's roughly the same as fp2. Here it's roughly the same as fp3, and so on. I use the very same principle now for the curve integral. That gets me then to this expression here. That's just the correspondence for the Riemann sum in the curve integral. Okay, with that in place, we now plug in a few values. So I take the sum of f gamma ti. So pi is gamma ti. Pi plus 1 is gamma of ti plus 1. Pi is gamma ti. With that in place, let's see what happens. So I got that sum here, function values at gamma ti, and then the difference, the length of this curved segment, gamma ti plus 1 minus gamma ti. Okay, without changing anything, I divide and multiply by gamma ti by ti plus 1 minus ti. And what I see here, this guy here, is roughly the same as gamma ti. Because after all, it's a difference quotient. It looks a bit like a difference quotient if I take the distance between ti plus 1 and ti smaller and smaller. Now we're interested in what happens if you take the difference between ti and ti plus 1 smaller and smaller. In the case of the Riemann sum for the standard integral, that gets us the value of that will get us the value of the integral by definition. If you now take a finer and finer resolution, if the distances between ti plus 1, and so on, if they get smaller and smaller, if I take a finer and finer subdivision of the parameter interval, then in the limit, this will look like the Riemann sum corresponding to some integral, namely, okay, this term here, this term will become, well, just f of gamma t. We take smaller and smaller we take more and more function values. And this term here, okay, what we see here is it looks a bit familiar to a difference quotient. So more precisely, I see gamma ti plus 1 minus gamma ti. if I divide this by the difference between the parameters ti plus 1 and ti, okay. The thing with the magnitude is I can pull in factors, and this division by ti plus 1 minus ti can also be pulled in. I get that expression here, gamma ti plus 1 minus gamma ti divided by ti plus 1 minus ti. Now you see, inside this magnitude, I've got a difference quotient. It looks like a difference quotient. And as the difference between ti plus 1 and ti gets smaller and smaller in the limit, I get the magnitude of the speed. So in some sense, that's the mathematical justification. That's the mathematical justification for that definition of the curve integral. You can justify it by some physical intuition, namely that depending on the parameterization, you should introduce speed as a factor. But this is a purely mathematical justification for the definition of the curve integral. So we had some numerical examples, we had some mathematical background. I would like now to finish the discussion of integrals of functions along curves with two more examples. What are applications of curve integrals? North of Milano, there's a Giacomo Valley, the San Giacomo Valley. And within that valley, people do geological surveys. And for example, they're interested in the rock density there. Like, what is the density of the rock? Because it's still in the Alps, so people care about, okay, how difficult is it to make a tunnel underneath? So that map here illustrates a rock. It's a domain in art. It's a two-dimensional map, and on this map here, you've got a scalar field. Let's call it F, that describes the rock mass density. Generally speaking, if you've got areas that are painted in red, in reddish colors, it means that the rock mass is very high. But in the areas where you've got blue, the rock mass, the density is very low. If you want to drill a tunnel, then you care about how difficult is it to drill. For example, if the rock mass is very low, that will be easy. The costs of drilling there will be very low. You can do it fast. The drilling machines do not get exhausted too much. But if you go through an area with very hard rock, it will take more time, it will be more costly, and you need to refurbish your gear every now and then because it's detrimental to the quality of your machines. If you now want to plan a tunnel, how do we do that? Generally speaking, we can describe a tunnel by a curve. Let's say I want to drive a tunnel starting here and finishing like that. There could be a proposal for a tunnel. Maybe not a good one, but just one proposal. You would like to know how difficult is it to draw a tunnel there. You can describe this in terms now as a curve integral. So we've got this function f that describes at every point the rock mass density. And let's say we've got a curve gamma, and we parameterize it from 0 to 1. We could take any other parameterization, but we just pick 0 to 1. That describes the path of a tunnel, well, let's say it's 20 meters beneath the surface. Then the effort in excavating the tunnel can be described roughly by a curve integral. Namely, we integrate the rock mass density along this curve. That will roughly tell us how difficult is it to excavate a tunnel there underneath. So how long does it take? How much energy do we need? And what is the wear and tear on the machines? Then given the rock mass density and this parameterization of the curve, we can compute that value. Typically, how geologists derive the maps like this is they make a few measurements, and then they say, okay, we have like maybe 100 measurements, and then we estimate a function based on those measurements. So lots of interesting mathematics goes in there, how to make such accurate maps. And we notice the value of this integral here, the value of the curve integral should not depend on the parameterization at all. We could take a parameterization from 0 to 1. We could take a parameterization in terms of kilometers, in terms of miles. That should not make any difference at all. That's one real-life example where you could apply curve integrals. Let me do one more example that is slightly different. That is a map of San Francisco, and it describes the crime density of San Francisco. So like for every American city, you can find easily such maps that tell you, okay, for example, in this area here, you've got a very high crime density. Let's suppose you take the bus from the airport and you get out of this area. And you want to get to and your hotel is up here. Okay, you need to find some path going from the starting point to the end point. What is a good path to walk? I mean, I'm not saying that you walk in San Francisco, but let's pretend that you walk. Let's say we have got a function p. Let's say we got a function p that models the crime density. If you walk along any curve, then, roughly speaking, the curve integral of the crime density will tell you what is the probability of getting robbed, for example. So let's say you walk along some curve to your hotel. Then you can compute the curve integral of the crime density, and this will roughly tell you how safe is it walking there. Is that path a good idea or not? And even if you don't do this when you are in San Francisco, but perhaps you at some point develop an app that does precisely such a calculation. How much time do we have left? A few minutes. Okay. That will finish the discussion of curve integrals, but let's get warmed up with something else, namely curve integrals along vector fields. We just do one example, the last few minutes, so you've seen it and can think about it over the weekend. Suppose that we have got a train, and the train moves along a path gamma t, along a path gamma. It's defined over an interval from a to b, and let's say it's not r to the v, it should be r to the 2, of course. You've got this train moving, but it's very stormy weather, so there's some wind blowing, and of course the wind exerts some force onto you. Depending on the direction of the wind, it may obstruct your movement, it may be a force against your movement, or in the opposite case, it may actually it might be a force that actually helps you moving forward. Now let's say you are as a train driver, as a train conductor, then the question is, okay, how does the wind actually influence your movement? How much force do you need to conduct this movement? Now, if you've got this curve here, if you've got this curve gamma t, and let's say in our surroundings, you've got a force field F that describes the wind. then, okay, we do the following simplification. We say that there's no friction, meaning if the wind blows from the side, there's no friction or anything, it has no effect at all. So if the wind keeps blowing from the side, it has no effect. But if the wind, for example, keeps blowing from behind you, it accelerates you. If the wind blew in the opposite direction, it would decelerate you. What you do is you decompose this force field into the tangential component, parallel to the tangential component of the curve, and the orthogonal component. And in that simplified model, only the parallel component will matter. And that gives rise then to the notion of curve integrals of vector fields. Next lecture, we go deeper into that.